To examine a converging lens, try putting the lens in a screen on rails and aiming it out the window. The red labeled lens is the shortest focal length, so it'll be easiest to use to get a bright image. If it's bright enough day outside, you can use the building across the street as your object at infinity. If you have the screen about a focal length away from the lens, you'll be able to see the inverted image of the building outside focused on the screen. You can replace the red labeled lens with a green labeled lens with a larger focal length to see an image with a higher magnification. To measure the focal length of a lens, this is what we'll use. We'll place a light source at the 0 mark on our set of rails and a screen 30 centimeters away. We'll measure the focal length of the red lens by using it to form an image of the light source on the screen. Slide the lens back and forth and note when we have an image in focus on the screen. From these values, we'll be able to calculate the focal length of the lens. When we move on to telescopes, we'll use the long focal length lens as our objective lens and the shorter focal length as our eyepiece. Point the setup outside an object far away. If you look through the objective lens, you'll see the object inverted. If you look through both lenses together, you'll see the image is still inverted and now magnified. Lastly, here's our model of the human eye. There are slots for lenses on the outside which we'll use to model external corrective lenses. The inside is filled with distilled water to model the vitreous, and slots for lenses at the front of the eye represent different positions of the eye's crystalline lens. The screen at the back is the model's retina, and it's movable away from or toward the lenses, which we'll use to model near or farsightedness. If you point the eye model at a bright object, you can adjust the lenses to achieve an image in focus on the retina.